Welcome to Microlecture 52 on alkene addition reactions. This one is epoxidation. Okay, so the next reaction here is the addition of MCPBA, which is a peroxy acid to cause epoxidation. You've heard of epoxides before, an epoxy glue. This is the functional group involved. It's a three-member ring with oxygen in it, and we want to be able to draw a concerted curved arrow mechanism between the alkene and the MCPBA structure, and I'll show that last. And we want to be able to predict the stereochemistry, syn or anti, and predict whether the product is chiral or achiral. So what is going to happen with these reactions is that the double bond is going to break, and in its place of one of the two bonds, we're going to have an oxygen atom add across both carbon atoms so that we end up with a three-membered ring. Of course, there's only one way to add one atom across a carbon-carbon double bond, and that's going to be syn. You can't add one thing to both sides of the carbon-carbon double bond simultaneously. So the proper way to draw this is for both bonds to be on the wedge or with equal likelihood, and that would force this methyl to be on the dash. With equal likelihood, we could form the epoxide with both bonds on the dash. This is a 50-50 mix. Well, this is not a stereocenter because there's two methyl groups attached. However, here we do have four unique groups attached. So there is a chirality center, but we kill chirality because the other enantiomer can form at that site. So we get a 50-50 mix of enantiomers. And so the product is achiral. So let's predict a couple of more examples. Here we've got a nearby R group situated on the back face of our molecule. That means that MCPBA, which is this, by the way, it's just another way to write MCPBA. Let's talk about that real quick. MCPBA looks like this. Okay, and so this oxygen connected with a carbon oxygen double bond is called a peroxy acid group. And another way we can write that then is to just abbreviate this whole thing over here as aryl. It's an aryl ring, a decorated benzene. And so we can have aryl CO3H, which is what we're seeing as our reagent there. We can have aryl COOOH. So there's three oxygens actually, sort of in a row, if we represent it that way. And if we see three oxygens on a carbon, then we know it's a peroxy acid, and a peroxy acid is going to react like MCPBA. So either one of these, if you see them, just sub out for MCPBA. You know it's going to react exactly the same way. All right, so this is the same reaction we saw on the previous slide, except this time we've got an R group preventing approach on the back face, the dash face. All right, so that means that the epoxide is going to form on the opposite face, which means actually this drawing makes very little sense actually. We can think of it this way first and then redraw it to make sense. Okay, so let me redraw this. Okay, so what that means is that the ethyl's over here, and the group with the epoxide is also this way because that bond has to be on wedge. All right, so it doesn't matter so much that we show the epoxide on wedge so much as that we show the nature of that center right there. All right, and it's counterintuitive because it's going to force that bond to be on the same face as the ethyl group, but that's the only way that the MCPBA can approach, is on the opposite face of the ethyl group. All right, so we predict this as our expected epoxide product, and that drawing makes a bit more sense than the original one that I drew, because for any tetrahedral center, we have to have two planar bonds, one dash, one wedge, right? And in this case, we have three planar bonds, okay, on this carbon right here. We have three planar bonds and a wedge. So we wouldn't be able to determine an absolute stereo configuration, R or S, if it's drawn this way. We have to be able to draw that into a more sensible way so that we could determine whether that center is an R center or an S center. Okay, and so the last example here, I'm seeing a perfectly flat structure. There's nothing nearby on dash or wedge that's going to prevent the approach of the molecule from one face or the other. I'm going to redraw the benzene ring. It's not reactive. And I'm going to draw the epoxide forming on one face, and then I'm going to draw the epoxide forming on the other face, and then I'm going to fill in the details so that everything makes sense, right? Going back to the top, my methyl group has to be shown as either dash or wedge. I've got too many planar bonds, so I'm going to redraw that methyl so that I can determine the stereo configuration at that site if I wanted to. And then I'll do the same thing with the methyl group on the bottom. And what we see is we've got a 50-50 mix of enantiomers. So it's achiral. Whereas with the previous example, we had only one possibility. It was chiral. Of course, we started with something that was chiral, so that makes sense. Right, so two possible products for this latter one possible product for the previous problem. So the mechanistic details, this is another cyclic concerted mechanism. And so what's going to happen is that the MCPBA molecule is going to approach the double bond. Let me draw out the MCPBA molecule again. So there it is, and the mechanism works this way. The double bond is going to attack the OH oxygen, which is going to circle around then with its bond to hydrogen. And so I'm going to kind of go all the way around here to grab the oxygen atom. I'm going to form an OH bond there. The electrons from the carbon-oxygen double bond kick inward this way to form a carbon-oxygen double bond there, and this very weak oxygen-oxygen single bond breaks, giving that oxygen atom to the carbon-carbon double bond. So that's how one oxygen atom adds across the carbon-carbon double bond. Okay, so the result is that oxygen atom has added, to one face across the double bond, forcing this stereochemistry. Of course, we could have ended up with the opposite scenario if the MCPBA approached from the opposite face of the alkene. So if you're having trouble seeing which oxygen is which, it's this oxygen here that's added across the double bond. And the byproduct, then you don't have to predict. But if you followed the curved arrows, it makes sense that your byproduct here is a carboxylic acid. So I just wanted to add a note here that next quarter we're going to utilize this chemistry. So it might be a good one to retain. It's all good to retain, but the epoxide functional group is going to be used in a subsequent reaction with aqueous acid, so H plus and H2O, to generate dihydroxylated species that is actually trans. All right, so it's not at all like the dihydroxylated product that you get when we use osmium tetroxide. So remember, with osmium tetroxide, we get syn addition to get these cis OH groups. But here we can achieve trans, and so again, it's nice to have different reagent sets to accomplish different stereochemistries.